Thank you very much, Boris. It's a great pleasure for me to have a chance to come here and to discuss a little bit of my research activities. And so thank you very much, Boris, and Elena, Pavel, and Andrei, and all the others who made my visit possible. So we discussed for several years, but finally the time came. So thank you very much. So today I'm going to discuss some ideas and little results that we have on distributed randomized algorithms for social and sensor networks. So in a sense, this talk it's on the interface between social networks and technological networks, which are sensor networks. But there are some ideas related to control systems. So in particular, we're going to discuss two different applications. So first is so-called opinion dynamics in social networks, and the second problem that I got more interested in recently is a problem which I found fascinating, which is the problem of clock synchronization in wireless networks and also in other networks. And the kind of tools that we are developing are distributed algorithms of randomized fashion and also time averaging, which plays a key role. And from the technical viewpoint, we want to establish some properties which are related to ergodicity of stochastic processes. So in a sense, there are some technological motivations, but the results that we are looking for are sort of results related to stochastic processes. So first we are going to deal with opinion dynamics in social networks. And since there is the World Cup now, I want to pose a question. How much do you like soccer? And there are several individuals in this room, and here is the opinion of each individual in a scale between 0 and 1. So x is a numerical value which represents the opinion that each human has about a specific topic. For example, soccer. And here it's the time, whatever, you can think about seconds, minutes, hours, whatever. So it's the opinion on how the opinion of individuals evolve over time. And we are taking the viewpoint that these individuals, that these humans, are discussing the topic and they are exchanging information, and possibly they change and they adjust their opinion based on the opinion of others. So they discuss the topic, they discuss soccer, and maybe they are influenced by the opinion of others, and maybe change their mind sometime, or sometimes they don't change their mind. As you can see, there are different individuals. For example, a green individual. This green individual does not really have a clear opinion about soccer. His opinion is somewhat around 0.5, 0.7, and the opinion of this individual is changing a lot. On the other hand, there are other individuals, like this person. This person is very stubborn. He's really convinced that soccer is such a great thing, and his opinion is say, 0.95, and he talks to others, but others are not going to convince him or her that soccer is not such a great thing. So there are two different kinds of agents, and there are stubborn agents, like this one. This person is very stubborn. He or she talks to others, but he or she doesn't change his mind. So his opinion is constant forever. On the other hand, there are also other individuals, like this green person. He's very open-minded. And for example, he starts with an initial value here, which is what we're going to say, which is what we're going to call the prejudices that this person has. He talks to this blue person. He's somewhat influenced that soccer is such a great thing, so he actually increases his opinion, but then he talks to others, his opinion is going to, to decrease, and then there are lots of fluctuations. One important thing, I'm sure that you are aware of the research activities in the area of consensus, and here there is no consensus. So agents do not reach a common opinion. In consensus, which has been is still quite a hot topic, in particular in the US, in particular because of funding reasons, you have several robots, for example, and you want to reach a consensus between all these robots. So all these robots, they want to converge to a specific target. So that's consensus. And here there is no consensus. The final opinion that these humans have are quite different. In addition to that, there is not even a convergence of opinions. There is no convergence because, for example, these individuals, they oscillate around a certain mean value. And we want to establish some properties of these oscillations. Here it's an important concept that will come out from the technical viewpoint, but also from perhaps the psychological viewpoint or social viewpoint. We're not really interested in knowing our own opinion about a certain topic every minute. We want to see what is our average opinion over time. So if somewhat, we take some sort of average opinion over time, we see that we are smoothing opinions, and then we don't get these ugly fluctuations, and somewhat we converge. However, so with time averaging, we do not show oscillations, we converge on some final values. On the other hand, we don't really have consensus, as I mentioned before. So we have some sort of consensus, partial consensus in some cases. For example, these individuals, they somewhat converge to this common value, but this common value is only between these two individuals, and it's actually very different than the value of these individuals.
Roberto?
Yes?
Excuse me, just a question. Is this data like real data or it's synthetic data?
I'm going to show a specific. This data is an example based on a model that I'm going to discuss, which is the so-called Friedkin and Johnson model. So in particular, this one is not based on real data, but there are other examples based on this Friedkin and Johnson model, which are based on real data. So each agent reaches a stable opinion at some point. However, it's not a global consensus. So some agents aggregate into opinion clusters, others don't. So there are key differences to consensus of multi-agent systems in the sense that you don't reach consensus of all these individuals. So we only have some aggregation and some partial consensus. And there are some very interesting questions which are related to graph theory, how you cannot detect a priori how many clusters you have. And this clearly depends on the topology of the network. So this is the Friedkin and Johnson model that I was going to discuss. So Friedkin and Johnson are professors of sociology. Actually, Johnson is a retired professor at the University of California, Santa Barbara. And this is a sort of a well-known and classical model that was invented by Friedkin and Johnson several years ago. What I think is interesting about Friedkin in particular, Friedkin is a professor of sociology. Nevertheless, he knows dynamical systems, he knows graph theory, and to some extent. And so it's possible to establish a dialogue with him, and because he's using equations. There are lots of people in sociology who are discussing topics for pages and pages and pages, but for someone like me, I don't understand what's the point. I mean, with Friedkin and Johnson, it's easier to talk about because they write equations. So this is the Friedkin and Johnson model opinion. So it's a discrete time model opinions, which is it's a linear system, and X, which is the state, represents the so-called opinion or belief. And there are some initial conditions, which are called the prejudices, which is the input. W is a non-negative matrix, so all the entries in this matrix are non-negative, so non-negative in the sense of entry-wise, which represents the strength of interactions between agents. So if some values are larger, then it means that there are some strong interactions between the agents, between these individuals. And then there is another matrix that they introduce, which is a diagonal matrix, which is called lambda, and this represents the sensitivity of opinions of other agents. It's a diagonal matrix to see how sensitive they are. So they take W, a row stochastic matrix, so 1 is a vector of all entries equal to 1, so W1 is equal to 1, and they take lambda, which is the sensitivity, equal to identity minus the diagonal. So this is the Friedkin-Johnson. And in particular, we can discuss what is the opinion profile. We know how to compute x of k in terms of the initial conditions. We know that from linear system, it's obvious. And so this is the so-called opinion profile, what in sociology they call it opinion profile. So the opinion profile of agents is given by this very simple equation. And the first question, which is somewhat obvious at this point, is that the question is where the opinions converge to a stable opinion profile for k sufficiently large. So do we have convergence or not? And there are some very simple conditions that can be established for the Friedkin and Johnson model, which basically tell us when we converge. So the assumption is that for each agent L, there exists a path from L, from the graph viewpoint, path into the graph. For each agent L, there exists a path from L to I, such that the II entry of the W matrix is positive. So this implies that each agent is influenced by at least one stubborn agent. It's very easy to show that if the graph is strongly connected, so from everywhere we can go to anywhere into the graph, then this assumption is satisfied. So if you don't care about the matrix W, whatever, you see that there is an underlying graph in this Friedkin and Johnson model, and if the graph is strongly connected, then this assumption is satisfied, and this is a sufficient condition to establish convergence of opinions. And convergence of opinions is given by this very simple equation. So for k sufficiently large, x of k converges to what we call x opinion dynamics, and it's given by this equation. So in other words, this matrix is full rank, so we can take the inverse, and then we can simply compute this. So let's run this simple example that Giuseppe was asking for. So in this case, we have a priori conditions. This is an example generated by Friedkin and Johnson. It's a very simple example of 4 agents. So the prejudices are the following. So there are 4 agents, 4 individuals. The first individual here is they are not normalizing the interval 0, 1, but you can divide by 100. And so the first individual has an a priori opinion about a certain topic, about soccer, which is say 25. The second one is same value, and the third one is 75, and the fourth one is 85. So these 2 guys have a larger value than the other 2. And this is the strength of interaction W matrix, which is, as I said, it's a metric which is positive in the sense that all the entries are positive, and it's a row stochastic matrix, so W times 1 is equal to 1. And then you take the diagonal, and the lambda diagonal metric, which is the sensitivity. As I said, the sensitivity, the identity, minus W. Here, immediately, you see that if you look at this one, you see that the agent number 3 is a stubborn agent. Because if you do just a simple multiplication between the matrix W and so on, you see that the fact that there is, in this row, there is only one element which is equal to 1 and all the others are equal to 0, it means that the agent number 3 is not changing his opinion. So we can simply plug in the numbers, and it's a straightforward computation, and you can actually compute this opinion dynamics immediately. It's a 2-minute computation in MATLAB, and this is what you get. Suppose that we do some plot, and this is what we have for this model. So the first 2 individuals, they start from point 25 and point 25, and they somewhat, diverge a little bit here, but, eventually, they come here. And basically, these 2 people have the same opinion over time. Okay? And they reach a partial consensus, because there is a consensus between these 2 individuals, but they don't reach a consensus with the other 2. The other 2, they start from different values. One is 75, and the other is 85. And you can see this red guy is a stubborn guy. He's the third one in our system. So the opinion of this person is stable forever. On the other hand, the opinion of this guy is somewhat influenced by the opinion of this red guy. So his opinion decreases, and then somewhat they converge. So this is the opinion profile. It's very easy to do this in MATLAB, of course. And then there is the red, stubborn, and cyan agents. They reach a consensus, and these 2, they reach a consensus, so there are 2 clusters, but there is not a global consensus. So global consensus is not achieved, and there are 2 distinct opinion clusters, which are formed. So far, so good. However, I would like to mention something which was quite interesting for me, which is a sentence which is borrowed from one of the papers by Friedkin and Johnson. So let's read this sentence, which discusses the model of interpersonal influences. It is axiomatic that this model of social influence will be imperfect at some level. So they basically realize that there is, the model is inaccurate as any other model that we have. It is obvious that interpersonal influences do not occur in the simultaneous way. So this is quite important from my point of view. Interpersonal influences do not occur in the simultaneous way. And there are some complex sequences of interpersonal influences in a group. It is clear that there may be short circuits in the process of interpersonal influences. So let me remark the fact that interpersonal influences do not occur in the simultaneous way. So what it means, it's an issue of global versus local information. So interpersonal influences, let me repeat again, do not occur simultaneously. So no global exchange of information. The agents discuss the topic within small groups. For example, in pairs or in triples. If all of us want to discuss a certain topic, say soccer, we cannot exchange information simultaneously between all of us. But at some time k, there are two of us, say for example Pavel and myself, who are talking about soccer, and then Andrea is talking to Pavel at time k plus 1, and then Boris is talking to Pavel, and so on and so forth. And an example that it comes out quite often in the work of Friedkin and Johnson is also the fact that, for example, when a human needs to take a difficult decision about health, for example, he has two options, either to take surgery or to take some medical treatment, this person does not want to discuss this problem with everyone into the world. He or she wants to discuss the problem, the issue, and to take this difficult decision within small groups, families or friends, small groups. So basically, we want to exchange, so there is no global exchange of information. We want to exchange information only within small groups. So so this is the model that we are going to discuss. So we consider a directed graph, G, which consists of vertices and edges. So it's a directed graph, we have lots of vertices, we have edges. And so we can discuss two different models. One is realistic and the other one is not realistic. We have a synchronous model where all the agents simultaneously exchange information through links. So all these agents, all these individuals, they talk about soccer at the same time. This is clearly impossible. It's just a mess if all of us are exchanging information at the same time. It's much more realistic in a synchronous model, which is based on a local communication protocol. Local communication protocol means that these two individuals are actually exchanging information at the same time, K. And then at the time K plus 1, then there are other two individuals who are exchanging information. And the graph, we take a directed graph, so which means that this person is talking and this person is listening, and there is an exchange of information between the two. So, and one motivation from perhaps the sociological viewpoint, it's an observation, that communications between humans are becoming increasingly asynchronous. And examples are text-based messages, email, bulletin boards, blogs, forums, and so on. They are delivered via web technology, and they are independent of time and place. A synchronous model, on the other hand, is phone and conference call, but this requires much more strict protocol, because humans, in order to have a conference call, for example, they have to agree on a certain time and place, which is actually more complicated, like the phone call that I have to make today. So because, lots of individuals have to agree on a certain time, and that's more complicated. So just a little detour on, because it comes out later, Monte Carlo and Las Vegas randomized algorithms. So Monte Carlo was invented by Metropolis, Ulam, von Neumann, Fermi in the 40s in the Environmental Manhattan Project. It came out in physics, and these are pictures of these famous individuals: Metropolis, Fermi, Ulam, Feynman, von Neumann. And Las Vegas, on the other hand, appeared in computer science in the late 70s. So the definition of a randomized algorithm, which is borrowed from computer science, is the following. It's an algorithm that makes random choices during execution to produce a result. So a very simple randomized algorithm is a random choice, so heads or tails with equal probability, and then we make a certain decision based on the outcome of this random choice. An example is the MATLAB code. So for example here, in this statement, we have rand, which is a random generator which we assume perfect, uniform in the interval 0, 1. If this outcome is greater than 0.5, then we execute this statement. On the other hand, if it is smaller than 0.5, then we go to this statement. This is an example of a randomized algorithm. There are two classes of randomized algorithms. One is Monte Carlo, that I'm not going to discuss here. Just very briefly, Las Vegas randomized algorithm. Again, this is notion introduced in computer science. So it's a randomized algorithm that always produces correct results. The only variation from one run to another one is the running time. So the key point, the key difference between Las Vegas and Monte Carlo is that Las Vegas you are dealing with discrete random variables. In the case of Monte Carlo, you are dealing with continuous random variables. And an example of Las Vegas is that suppose that you have a bunch of lights that you want to turn on. So they are discrete random variables. We say time k, with probability 1 over k, you turn on this light. Here, it's like here, we have lots of lights. And then at time k plus 1, you turn on another one, and so on and so forth. So you may need to wait for a long time, but you can turn on all these lights. And that's the key difference with Monte Carlo, because in Monte Carlo it's a continuum, so you cannot explore completely the search space. Here you can. So this is just a very brief introduction to randomized algorithm, just to tell you what is a randomized algorithm, and in a minute I'm going to explain the role that randomized algorithms are playing for our sociological programs. Before that, I want to mention that randomization in sociology is not a new concept. It has been introduced by Jon Elster, who is a professor of sociology at Columbia University. And Elster is talking about randomization in individual and social decisions. In particular, Elster discusses the importance of randomization for designing experiments. For example, when there is a need to decide which patients may be selected to receive a standard or a new treatment for a disease. It's important to notice that these people in sociology are somewhat influenced or obsessed by the concept of dealing with difficult decisions in life related to health. So what is the role that is playing randomization from our point of view? Well, from our point of view, we have a graph which consists of vertices and edges. So edges is the edge set. And we are dealing with a so-called Gaussian protocol, which is based on uniform edge randomization. I'm going to show it an example in a second. But basically here we are dealing with stochastic process. So it's a random process which evolves over time. K is the time. It means that it's a sequence of independent, identically distributed random variables. So at time k, with probability 1 over n, we basically pick an edge out of these possible edges. So, and then we of course need to establish convergence properties of this randomized Gaussian protocol. Let me explain a little more. So we have a bunch of individuals. Each individual is a vertex or a node in this network. And then there are edges which represent the communications between individuals. At time k, we select an edge at random with probability 1 over n, if n is the number of edges, and these are IID. Okay? So, which means that at time k, these two individuals communicate, which means that this person is talking, this person is listening. Okay? And then at time k plus 1, we select another edge. The gossip means that this individual is talking to his neighbors, because we are interested in discussing topics between friends. So this person is talking to this person who is close to him or her, and is not discussing with this person who is far away. So gossip interaction, it means that at time k, there is a directed link, ij, in the edge set, which is sampled according to a uniform distribution in the edge set. We take uniform just for simplicity. It should be IID. So at time k, agents I and j exchange information. Agent I updates its opinion based on its previous opinion. So at time k minus 1, and the opinion of agent j and the initial prejudice is v. So finally, after all this discussion, we have some equations. So what is the equation? The equation is the following. Agent I changes opinion based on interaction with agent j. So the ith element of x, of the opinion at time k plus 1, is based on the opinion of agent I at time k, and on the opinion of agent j, and on the initial prejudices, which is v. hi and gamma ij are given coefficients, which I'm going to explain in a minute. I want to remark that this formula is given by this portion here. This portion here, which is repeated here, is somewhat a convex combination between the opinion of agent I and the opinion of the agent j. And gamma ij is just a convex combination coefficient. So what's in the interpretation of this? This is somewhat an intermediate opinion between the agent I and j. Okay? And then we have a second convex combination, which involves this convex combination coefficient hi, and this is a convex combination between this intermediate opinion and the a priori prejudices, pi. And in this case, the convex combination coefficient is hi. So this is the equation that we have. So what is interesting in this equation is that, again, let me repeat, the agent I has an opinion which depends on its opinion at the previous time and on the opinion of agent j and the initial prejudices. All the other agents do not change opinion. Okay, so it's a Gaussian protocol, and it means that only this agent is actually changing its opinion. Also, so all the other agents are not updating the opinion. I want to mention that this is a somewhat asymmetric update of information between I and j, in the sense that I depends on itself and depends on j, and not vice versa. I mean, we can have different models if we wish. And these are just little equations, it's not really important to say what is this coefficient hi. And these coefficients hi are given by these equations which depend on the degree of the vertex I. So the number of incoming and outgoing edges. And it took a long time for us to find exactly this formula, in particular for this one. So these are the gamma ij coefficients. It took a long time to us to find this because what was giving trouble from the technical viewpoint was the case of stubborn agents. So we were somewhat able to solve quite easily the problem, but the case of stubborn agents was giving us lots of difficulties. So it took a long time to us, because perhaps we are slow. So, well, suppose that we just run this protocol that I explained over time, and we can see that this is what we get. So we have lots of undesired oscillations, which is not nice, because we don't have convergence. So the dynamics of the randomized Gaussian protocol, which I discussed, oscillates, and there is no convergence of the protocol. So that's bad. So we are stuck for a while. And then luckily, who helped us? So time averaging was introduced in the 70s in the rational literature to accelerate convergence of stochastic approximation algorithms. So thanks to Boris Polyak. And then I think that there was a subsequent paper by Polyak again and Anatoly Juditsky, which was published in Siam a few years later, which was basically exposing these similar ideas into the Western literature. Well, what about if we take averaging? If we take averaging, of course, we slow down convergence, because now convergence is of the order 1/k, but then we are smoothing oscillations. And so basically we don't have oscillations anymore, we have convergence. So with time averaging, average Gaussian opinion, we remove oscillations. And so we have convergence. And in fact, we have a little theorem here, which tells us exactly the following. So this is a theorem with Paolo Frasca, Chiara Ravazzi, Deakishi, and myself. These are just preliminary results, very recent that they came out. It's not even published in the journal. So, assuming that the graph is strongly connected, which is what we discussed before, then the time average local opinion, y of k, after averaging, are mean square ergodic and converge to x opinion dynamics in the following sense. So x opinion dynamics is given by this formula that I discussed a few minutes ago, and so we have ergodicity properties of this protocol in the following sense. It's not too hard to prove, there are some technicalities and so on. Basically you have to prove, we basically followed sort of a brute force approach. We compute a bound on the expected value squared, and then we show that this bound goes to 0 for k becoming larger and larger. Of course, the question is that can we prove other properties? Not only mean square ergodic, other properties. And in fact, yes, we can. Other convergence properties are stronger. For convergence, we can also prove convergence with probability 1. And the simple observation is the following. The randomized Gaussian protocol is a so-called Markovian jump system. And so we know that mean square for Markovian jump systems, mean square ergodicity imply convergence with probability 1. And so we have other properties on this protocol. The questions, of course, one can pose the question. I don't have a full answer yet, so this is why I'm just posing this sort of a research problem. And the question is, what are the prejudices so that the opinion converges to a given value? So this is like the inverse problem to the Friedking and Johnson problem. So in the case of Friedking and Johnson, they know some a priori prejudices and they want to compute what are the opinions. And here is just the opposite. So suppose that you have an a priori, you have an a posteriori opinion, and then you want to establish what are the prejudices so that this is what you get. So it's like inverting the Friedking and Johnson model. Assuming that all the agents have some degree of obstinacy, which basically means that this matrix is full rank, in this case, I mean, the answer is very simple. It's just inverting them. And so the prejudices are given by this formula, which is very simple. So you can actually plug in numbers, and this is what you have. So for the previous example with 4 agents, you can actually do some easy computation. You can see that the matrix is fully controllable, so the controllability matrix has rank 4. And given these opinions, for example 30, 10, 25, 50, then we obtain the prejudices which are equal to this. One important remark here is that the prejudices, some of the prejudices are negative. And so I discussed this with Friedking. Does it make sense? And he says yes, according to definitions in sociology, the prejudices can be also negative. I mean, you have not necessarily you have only positive opinions, but you can also have negative opinion about a certain topic. So which is even more enforcing the negativity. So anyway, this is, according to sociologists, this makes sense. Well, there are some other ideas here and that we can discuss here, but one point that I don't know yet how to solve it, besides uniqueness and things like that, which are easy to discuss, this protocol for controlling opinions is fully centralized, so it's a synchronous model. So how to control opinions in a synchronous model, I don't know yet. So I want to spend a couple of minutes discussing some references. Well, this is the paper that Giuseppe Fabrizio, the book that Giuseppe Fabrizio and myself wrote, and this is the second edition. It's on randomized algorithms. In particular, if you are interested in Las Vegas randomized algorithms, a paper by Leaki, Ishii, and myself, a few years ago in European Journal of Control. And there are 2 papers that I want to mention. One is this proceedings of IFAC Nexus, ergodic randomized algorithms and dynamics over networks, and we also have an archived version which is still submitted for journal publication. There are other models in sociology which are used, for example this one by Higuang Kung from Chinese Academy of Sciences. This is a different model called the DW model. There are different models of opinion dynamics that people are discussing. So it will be interesting to try to find some sort of general solution. So before going to the second topic, and then I want to spend a couple of minutes on the second assignment for students. So opinion dynamics in social networks. So what do students have to do? Well, first example is Friedking and Johnson model with 4 agents, which is exactly what I discussed. It's a sort of training for the second example, which is to deal with a sparse social network with, say, 100 agents. So for the second one, you basically go into MATLAB, you build up a sparse matrix, W and so on, and then say, 100 by 100. So the answer that you have to address is to compute the true centralized solution, which is easy. It's just, matter of computing matrices and the inverse. And then the second one, you have to compute the distributed solution provided by the randomized Gaussian algorithm. Okay, and you have all the equations, so it should be easy to implement those in MATLAB. You can compute the mean square error between the true centralized solution, which is this one, and the distributed randomized solution, and then you can see how the mean square error evolves over time. And you have to see that, if the theory that I was presenting is right, which I think it is, for k sufficiently large, this mean square error goes to 0. And then you have to study and discuss the importance of randomization and time averaging. So without time averaging, you should see these undesired oscillations, but thanks to time averaging, then these undesired oscillations go away. So these are the first set of questions, and then there are even more interesting questions. Can you improve speed of convergence for other values of the coefficient of the randomized algorithm? I'm giving you some equations which are the coefficients h and gamma. You can plug in this, but then the question is that suppose that you use other values of the coefficients. Can you improve speed of convergence? So that's one question. The other question is that suppose that instead of taking uniform edge randomization, you take non-uniform randomization scheme. Can you improve speed of convergence? And of course, I'm not expecting you to give a theoretical answer. I'm expecting you to give some sort of simulation-based schemes which provide better speed of convergence. And then overall, I guess that's the main question that you have to address and answer in your presentations on Thursday. Study and discuss pros and cons of centralized and distributed solutions from the computational viewpoint and from the viewpoint of social network. So, from the computational viewpoint, assuming that you can implement this model, that's it. Nothing else. I mean, you just need to compute a matrix, compute the inverse of the matrix, and then the product between two matrices, and that's it. However, this model is not realistic, because this model assumes that you have a full information about the system. And basically, you are working with a synchronous mode, which is not realistic from the point of view of social networks. So you are working with an asynchronous model, which is based on a local communication protocol. At time k, Boris and myself are talking. And then at time k plus 1, Boris is talking to Pavel, and so on and so forth. So this is much more realistic. However, I mean, the drawback that we have, due to the fact that we need to introduce averaging, then we are sort of slowing down convergence. There are lots of open questions that I'm actually very interested in. And one of the questions is that suppose that now we take some sort of weighted averaging, or we take some parameters, so instead of averaging, we take some parameters which are decreasing. That's another way which is used in stochastic approximation methods. But then this parameter is a global parameter, which should be known to all the agents. And this is not realistic again. Of course, I will be happy to discuss with you offline anytime these two questions, so in case you have some specific questions to pose. So again, so Friedke and Johnson model for agents, that should be very easy. You will have the slides and then you have the paper also. The paper is this paper. I have a copy of the paper, electronic version of the paper. And then you build up a sparse social network with 100 agents. You pick any one you want. You just go to MATLAB and use the command for generating sparse matrices. For example, 100 agents. I will be very interested in to see what happens. We never done simulations for very large matrices. So if you have matrices with 1000 by 1000, what happens? I don't know. So compute the true centralized solution, compute the distributed solution provided by the randomized gossip algorithm. You have all the equations, so it should be easy to implement it. Compute the mean square error between the true centralized solution and distributed randomized solution to see how this mean square error evolves over time. And then study and discuss the importance of randomization and time averaging. Without time averaging, you have these undesired oscillations. Can you improve speed of convergence for other values of the coefficients in the randomized algorithm? Can you improve speed of convergence using different randomization schemes, non-uniform? Which one you pick? I mean, you can pick some edges more often than others, but which ones? And overall, study and discuss pros and cons of centralized and distributed solution from the computational viewpoint and from the viewpoint of a social network. So it's a more realistic one. I guess this ends my first point, my first part of the talk. And then I can move on to...
maybe let's have some questions to this part.
Sure, sure. If there are any questions now, or we can discuss
instance, there are some, I guess there are some technical details. Andrei, where students can find all the data?
On our school website?
It is not yet, but
because the 4x4 example, you have the slides, you will have the slides, and you will have the paper. So, I mean, for the 4x4, it's there. So it's on the slides.
okay. So slides will be available on the website of the school. Yeah.
I can give the slides right after the end of my talk.
Okay.
And for the 100, I mean,
Yeah.
you just randomly generate.
Sure.
And also I can give you the paper, so they can actually use the paper and the slides.
And Roberto, just
And of course I'm available anytime for answering questions or trying to help you. Also there is a MATLAB code which I gave to Yelena, which actually implement this, but I don't want to give you the MATLAB code because you have to write the MATLAB code. But we have the MATLAB
it's
code.
not a problem for them.
No, for sure not.
Okay, and Roberta, a short comment about
Please.
averaging.
Yes.
Thank you so much for mentioning my name, but it was absolutely not me who was the first to exploit time averaging in, say, in optimization. Arkady is here, and he was the first, say, it was Cesarov medium. So probably Cesarov was the first who used this averaging. So it has a long story.
But it's very interesting how this also propagated. I visited the Chinese Academy of Sciences a couple of times in recently. I discussed this with Lei Guo, Han Fu Chen, and so on. It's very interesting how they were inspired by ideas from the Russian literature on average. And they used also for discussing convergence of stochastic approximation algorithms in different forms.
That averaging was very socialistic idea.
But not time averaging. It is social averaging. Yeah.
But what I personally find interesting is that you came out with the ideas of averaging a long time ago, but I don't think at that time you thought that ideas of averaging could be used for social network or for wireless sensor networks and so on. So that's I find an interesting application of these ideas.
Извините, значит, вот здесь у нас появился новый участник нашей школы, гость, вернее, Аркадий Семенович Немировский, которого вы, конечно, знаете по работам, вот он лично здесь присутствует. Okay, sorry.
Thank you very much. So different problem, but similar ideas with some differences. So the problem is clock synchronization in local area networks or wireless sensor networks or wide area networks. So we study clock synchronization, and the viewpoint that we take is a viewpoint related to distributed computations. So we need to develop some tools from distributed computations. And I want to mention that there are different research activities regarding synchronization of oscillators, the so-called Kuramoto problem that came out in physics. And there are very interesting applications from the point of view of people having Parkinson's disease. And so this is completely unrelated line of research. So the tools are completely different. So study clock synchronization from the point of view of distributed computation. So what is the problem? The problem is that we have a network which could be a wireless, a wide area network or a local area network, and each computer connected in a wide area network or a local area network has its own local clock. And there is no global clock. And there is no global clock, and this is actually an undesirable thing, so we need to synchronize the local clocks of each computer. So that's the problem. Each computer, and they are connected through the network, and each computer has its own local clock, and there is a problem of no global clock, and we want to synchronize the problems, how to synchronize all the clocks. The point of view of discussing global clocks versus local clock has a long history, also in distributed computation. Perhaps one of the first papers, it's always hard to say who was first, but perhaps one of the first papers was a paper which received a lot of attention in the computer science literature by Leslie Lamport and others. Then Lamport moved to different things, in particular he worked on LaTeX. But at that point he motivated the problem, which is what is so-called the Byzantine agreement problem. So there are a bunch of generals, which this is the paradigm, a bunch of generals which are surrounding the city of Byzantium, and each general has to decide when to attack the Sultan who is in the city of Byzantium. And you have to find an agreement between all these generals, and the problem is that you need to have a global clock. Otherwise you cannot decide when to attack or when to retreat. So this problem has a very long history. The same problem comes out in wireless area networks. And for example here, we have a forest, and we can think about having lots of sensors around. And these sensors are deployed into the forest, and this is actually done very often for many applications. For example, for monitoring fires. And then the problem is that each sensor has its own local clock. And how the local clock of this sensor here can be synchronized with the clock of this sensor there. And that's a very serious problem. And it's actually very interesting also from the more fundamental control viewpoint. The problem is that we need to compensate the clock. So computer or sensor clock compensation. So the clock of each computer or sensor is generated by a quartz. Now the quartz has some changes, and these are due to the temperature, vibrations, aging, manufacturing, voltage supply, and so on and so forth. In particular, I want to emphasize the temperature issue. So these are plots taken from sensors which are deployed in the mountains, in the Alps, in the Matterhorn area. In the Alps, and not only in the Alps, there are lots of sensors around, for example, for monitoring purposes, because you want to check, Matterhorn, the rocks are fragile, and so you want to check, for example, if there are some fragile rocks which could fall down, and we can actually create problems to the population. So there are lots of sensors which are deployed in the areas. The problem is that temperature, these are data corresponding to a couple of years back in the month of November. The temperature actually can change between, say, minus 15 centigrades to plus 20. And there are huge oscillations every day. And so clearly there are lots of changes into the temperature. And these, of course, affect the clock. So it means that the clock of each computer is clearly depending on the temperature, and the clock is actually changing. And this actually gives a problem how to synchronize the clocks of all these computers, or all these sensors. Well, you know, the first idea that you can say is that what about using a GPS? Well, this is not realistic according to experts. I'm not an expert on this, but I talk to experts, and this is not really realistic to use GPS. First of all, because GPS requires high power and it is battery consuming. So if you have lots of sensors deployed into the forest there, the GPS, access to the GPS system requires a lot of battery. So what about if after 6 months, one of the sensors into the forest runs out of battery, then you have to change it. And this is time consuming, costly and so on. So you want to consume a minimal amount of energy. Also for GPS you need a special hardware, GPS antennas. 1,000 sensors up in the forest over there, and each of them needs to have its little antenna. This is not realistic. Well, also, GPS, you need a clear view to transmissions. So, for example, if you have a local area network, you don't have access to the GPS signal. From this point of view, mobility is an advantage. So also precision is not that good after all. There are other possibilities which are use the radio signals, for example, atomic clocks and so on, but these atomic clock signals are not available over a long distance. So we need to design something which is actually better than this one. There is a protocol which has been established by IEEE, which is IEEE standard 1588, which this standard came out in 2002. And this is so-called PTP, Precision Time Protocol. And it's actually interesting to read the description of this protocol. A protocol to synchronize independent clocks, so independent clocks, running on separate nodes, so each node into the network is a computer or a sensor, whatever, and so running on separate nodes of a distributed measurement or control system to high accuracy and precision. Later on, more recently, there was an extension of this protocol which came out in 2008 for more sophisticated communication mechanisms like end-to-end, peer-to-peer, intelligent switches and so on. Anyway, PTP defines how the protocol works, so message exchange for synchronization. However, PTP does not define the control algorithms, and that's good for us because we have a lot of room to design the control algorithms which could be implemented in PTP. So what is the point? The point is the following. Here you have this simple clock, here you have the real time, and here you have the local clock time. If you look at this one, this is an ideal clock. So which means that the local clock time coincides with the real time. Unfortunately, this is not going to happen. So you have, for example, the node A, the sensor A, this different slope, and so you have alpha and beta. Beta is the slope, which is no longer equal to 1, and this is what is called the drift, and then there is an offset, the fact that it doesn't go to the origin. So there is an offset and then there is a drift, and this corresponds to the clock A. Then you have another clock, which is clock B, which is here in red, and you have another offset and another drift. So offset and drift, these are the two main points. Of course, at this point you have, if you use this model, which is basically what is done in PTP, you have a very strong assumption. And the very strong assumption which my colleagues in computer engineering don't like, you have linearity. But I have to make some assumption, otherwise I cannot get that. So we assume linearity of time drift and offset of clock. So no global clock in LAN or wireless sensor networks, we only have local clocks for each sensor. So we assume linearity of time drift and offset of clock. There is, in PTP, there is a sort of technique which is called message passing. Message passing, it means that this represents clock I, this represents clock J. So there is a message passing containing a timestamp Ti. So timestamp Ti, then it means that the sensor I communicates its local time Ti to sensor J. And it's received, so it's sent at time Ti, and it's received at time Tj, which is not known exactly. So this is between the clock I and the clock J. And then you can imagine that there is another clock, which is clock K. So at the same time Ti, it's a broadcasting technique, so we sent out the signal, which is now received by clock K at time Tk. So this is a message passing technique. So, and then we can write some equations. So at time Tk, the sensor K receives the timestamp sent by sensor I at time Ti. So tk is alpha ik ti plus beta ik plus eta k. Alpha ik and beta ik are drift and offset, and eta k is measurement noise. Okay, and this involves the sensor k. So we can write a similar equation involving the sensor j. So a very similar equation. And then we can simply subtract the two equations, and then we can compute the relative time difference. The relative time difference is Tj minus Tk, and it's given by the difference of alpha ij minus alpha ik ti plus beta ij minus beta ik plus eta j minus eta k, which I combine into some noise which I call eta jk. So we get a linear equation of this form. From the point of view of graph, so the sensor I has a timestamp ti, which is known, so it broadcasted to sensor j and to sensor k, and this is the receival of the time of the message, and this is the receiver of the message, and we don't know Taj and Tak because this is actually very difficult to acquire this information, but we know what is the difference of Tj minus Tk. So we can assume that we have the relative difference between the two sensors, between the two times. So individual times Tj and Tk are unknown. However, we can collect noisy measurements of Tj minus Tk of the relative time difference. So the sensor j and the sensor k know the timestamp ti when the message was sent. They don't know when it is received. You only know the difference between the two. So the problem can be formulated using oriented graph G consisting of vertices and edges. So the sensor I is the message center with timestamp ti. We only look at the edges connecting the sensor j and k. And so, we can rewrite everything into a matrix equation, and then we get a nice linear equation. So here we have this nice linear equation is written in terms of B, AS plus eta. So what is B? B contains the time difference Tj minus Tk, which we know. And then we have this matrix A, which is known, because it consists of -1, +1, and so on. And then it consists of Ti. And Ti is when the message is sent. So Ti is known. So the matrix I is known. Tj minus Tk is also known. So B is known, A is known. What is not known is the vector S, which contains all these drifts and offsets. And we want to estimate this S value. And then we have additive noise, which is eta.
So this model assumes that we have some kind of one ideal sensor Ti which always shows the correct
Indeed.
time, right?
The message passing, that's exactly right. Ti is known, which is sent out. Of course, there are different kind of protocols within PTP. So one is, for example, there are different layers, and one is a so-called master and slave model. So in the master and slave model, you assume that I in this case is the master, and then J is the slave, which received the receipt. But you are absolutely right. So Ti is known. What is not known is Tj. What is not known is Tk. But you can measure the distance between Ti and Tj,
yeah.
Tk and Tj.
Thank you.
So in matrix form, we write a linear equation. B is given data, so noisy measurement or relative time difference. A is given matrix with timestamps, and all +1 and -1. S is unknown, clock, offset, and drift. And eta is measurement noise, including randomness. So as I said, here we have a sort of if you wish, a strong assumption. And the strong assumption is that you assume linearity of time, drift, and offset of clocks. I've seen papers by people in computer engineering where they don't assume linearity, then they get very ugly equations, and then of course they can only get with some sort of minimization algorithm, they can get a local solution, and there is nothing that is really meaningful from that point of view. So on the other hand, here we assume a model that linearity of time drift and offset is actually a serious assumption, exactly for the reasons that I said yesterday, that I said a few minutes ago, because we have temperature, for example, variations of temperature and so on. So linearity is a strong assumption, which could make sense in some cases. Well, in matrix form we write a linear equation. What is just a little more about these parameters entering here. B is, what is the dimension of B? Is the number of edges in this network. And S is twice the number of vertices, twice because we have offset and drift. And so, of course, well, posedness requires that we have a number of edges which is at least twice the number of vertices. So eta is random noise. For example, you can assume that it's Gaussian with mean value equal to 0 and identity covariance. And then the optimal clock synchronization is just a least square solution. So we minimize the least square solution of this one. Okay, so that's very, very simple. And here, for the next few minutes, I'm going to focus on a specific case just for simplicity. And the specific case is that assume that the drift is known. So if the drift is known and we estimate only the offset, A is the incidence matrix of the graph. And the incidence matrix of the graph, for example, if you have a graph here, like this one, then the incidence matrix can be easily constructed. And then, in order to compute the least square solution, you have to compute A transpose A, which is the Laplacian. And A transpose A, in this simple example, is given by this equation. Now, we have to take into account that this matrix, in this simple example, is 5 by 5, but this matrix is rank 4. So A transpose A is not invertible, so we need to take the pseudo-inverse. So the solution of this clock synchronization problem is the pseudo-inverse matrix of the Laplacian times A transpose B, because it's not the Laplacian is not full rank. Well, if you plug in numbers, then this is what you can do. Okay? So from this point of view, everything is simple. You formulate these clock synchronization problems in terms of finding a solution of a linear equation. You get the least square solution, and everything works. Well, what's the drawback? Well, the drawback is that, again, it's the same drawback as before. You cannot really work with the entire network, because working with the entire network is not a realistic assumption. Again, you want to take into account some sort of protocol which is based on randomization. And here the motivation is also very strong. It's a so-called green network approach. So green network approach, it means that you are basically activating only some of the nodes using randomization. So at time k, there are only 2 nodes which are actually activated, and all the other nodes asleep. So, which is, I think it's a great idea from the point of view of minimizing the battery consumption. So you don't want to have a lot of battery consumption. Think about, again, lots of sensors which are deployed into the forest. Here there are only 2 sensors at time k which are working, which are exchanging information. And so all the other nodes, what are they doing? Well, all the other nodes are sleeping, so they don't consume energy. So from this point of view, the idea is activation of nodes using randomization, and we activate only a small subset of the node for reducing energy consumption. All the other nodes are sleeping. So most of the nodes, most of the time, are doing nothing. So the key idea is to build up a distributed randomized algorithm. And so for each vertex I, for each sensor, vertex is a sensor, it's based on a triple of states. So we need to perform 3 different operations. The first operation is a row estimate. The second operation is a counter. And the third one is again averaging. So let's look at these 3 different steps. So we are dealing with the sensor I, the vertex I, and then the vertex I is a row estimate of Si obtained again through gossiping. Gossiping, it means that the sensor I is exchanging information with the neighbors. So, gossip protocol, again based on uniform edge randomization, or could be IID in general. So again, we take a random process, a stochastic process, so in the edge set. So theta k is a sequence of independent identically distributed random variables, which are basically telling us when the sensor I and the sensor j exchange information. And this is, these are the equations. So at time k, we take theta k in the edge set, so which means that we are activating the sensor I and the sensor j. All the other sensors are sleeping. So the sensor I, it's updating its own state through this simple equation. This simple equation tells us that the value of the sensor I at time k plus 1 is given by a convex combination between the value of the sensor I at time k and the value at time k of the sensor j. And the convex combination parameter is gamma, which is just in the 0, 1 interval. And then we take another parameter, which is bij. Bij is simply the ij, the 2ij entry in the vector b that we had before. And the sensor j is updated using a similar equation. Again, a convex combination between the sensor j and the sensor I, and then, with a minus sign here of this b parameter. Okay? And this involves the two sensors I and j, which are involved in this random process. All the other sensors L, which are not activated, are doing nothing, so they are sleeping. There are initial conditions in this equation, and gamma is any parameter in the interval 0, 1. So a key difference with the equation that we had before, there are some technical differences, but one difference is that this is any gamma parameter in this interval works. In the previous one, I established a specific value of gamma. So this is the raw estimate. The second one, which is actually important from this point of view, is the counter. This is like the clock. So we have the counter, which we call kappa I of k, which is the counter of the number of updates performed on the sensor I. So this counter is simply counting the number of times that the counter is activated. And the equation is actually very simple. So the sensor I, every time is activated, increasing the counter by 1. And the sensor j is increasing the counter by 1 because it's activated. So at this point we are activating two sensors, I and j, and so the counter of the sensor I increases by 1, and the counter by the sensor j is increasing by 1. All the other sensors are not activated, so there is no increase into the counter. So this is a dynamic equation which represents the local clock. As you can see, there is no global clock at all here. So this is a local clock. So the time index k counts the number of updates which occur in the network. The variable kappa I of k is the number of updates for the node I up to the current time. Kappa I is a local variable which is known only to each agent I, even if a global clock is not available. So remember that here when I discussed, when I introduced this problem, I said that there was an issue of global clock versus local clock. Here, the algorithm is totally asynchronous and fully distributed. So there is no need for a global clock. Here is just each sensor counts the number of updates. So it can be easily implemented at the level of local sensor. Suppose that we implement this, and then we get a mess. The dynamics of the raw estimates oscillates around the least square solution. So we need to do some averaging again to smooth this. And so the idea is to do some smoothing. So we have a smoothing estimate which is obtained through averaging. And we call this smoothed estimate y of k for the sensor. So these are the equations for the time averaging. It's simply the time averaging involving this equation involving the kappa I parameter, and it's kappa I of k plus 1 and kappa j of plus 1. So these are two equations involving the sensor I and the sensor j. All the other sensors are doing nothing. If you do this, then this is what you obtain. So dynamics of the time averaging estimate do not oscillate anymore. And in fact, we can prove a little theorem here. And the little theorem has very similar, in a sense, it's very similar to the theorem that we had before. Here we have also some ergodicity properties. So assume that theta of k, which is this counter, it's a uniform IID process. The time average is mean square ergodic and converges to this one. So again, here the point is that we can in principle compute a global solution, but then if we have a global solution which is this clock, then we have all these technological issues or also philosophical issues that I mentioned before. So with this y of k, then this is what we get. And then we get convergence in this sense. I think I'm getting close to the end. I want to mention that the problem that I want to work on is related to the issue of synchronization in the presence of so-called Byzantine sensors. So far we assume that the sensors they can be activated. So if at time k I turn on a sensor, then it works. Or there is, I want to study some extensions to sensors which fail to work. However, the kind of failure is a so-called Byzantine failure, so which is a very malicious failure. Because, for example, if a sensor does not work because, say, the battery, or there is a hardware problem, or there is a battery problem, then the sensor does not activate. But this is easy to detect. In that case, I can simply say, okay, forget about that sensor, it's broken, that's it. But now I want to study what is called Byzantine sensors. So in particular, there are faulty sensors which are hard to identify because they behave maliciously instead of simply crashing. A crash is very simple to detect. For example, you can check the battery or things like that, if you check if the signal is transmitted. But Byzantine sensors which may collude to maximize damage. And here I want to use some ideas that have been proposed originally by people in the computer science literature. As I mentioned, the issue of global clock versus local clock was proposed by Leslie Lamport in the 80s. But the problem was fully solved by Rabin using a randomized algorithm which had some very strong properties, convergence properties. How to use these ideas for this kind of problems into synchronization of clocks is not clear yet to me. In general, what from the more, say, theoretical viewpoint, and actually we have a draft paper on this, from the more, say, mathematical conceptual viewpoint, not from the technological viewpoint, we want to study a more general setting for affine dynamics of the following form. So we have an equation of this form, x of k plus 1 equal to p x of k plus u. So we have an input, it's a dynamic system, and then we consider an IID process theta of k, and then we can, given an IID realization of theta k, we want to construct a matrix, which is now becomes time-varying system, and then an input, which also depends on this IID realization, and then we want to study ergodic properties of this system. How to establish ergodic properties of this system. We have some results into this direction, which I think is interesting from the conceptual viewpoint. From the technical viewpoint, what are the similarities and the differences between the two problems that I was discussing? So I discussed two problems. One was a social network, and the other one was the problem of clock synchronization. From the mathematical viewpoint, the first problem is related to finding a solution to a linear system. So this is a linear system, X opinion dynamics equal to, call it this matrix H times V. So this is the global solution. So this is a linear system problem. The other one, so this is X, let me write it. Do I have a marker here? Oh, okay, perfect. So problem here is X opinion dynamics equal to a matrix H times V. This is a linear system. Okay? The second problem, yes?
Zoom a little bit.
It's okay. And we want to solve this problem in a distributed asynchronous way. The second problem is a minimization problem. So in this notation I want to minimize with respect to S of B minus AS squared. So this is solution of a linear system. This is a minimization problem. There is a third problem that I'm going to discuss tomorrow. Which is an eigenvalue problem. This is the page rank problem. So in a sense, all these problems fall under the same umbrella. This is a linear system, this is an eigenvalue problem, this is a minimization problem, and so on. They all fall under the same umbrella. However, I want to solve this problem, all these three problems in a distributed, randomized fashion using time averaging. So this is the general framework, and this general framework can be embedded into this problem. Some references. So for the clock synchronization, we have two proceedings papers. As I said, this research is very recent, so we have the paper which was published in the European Control Conference last year, and then there is also a paper published at the CDC. From the technological viewpoint, the solutions are there, but the motivations are quite different, because in these papers we were actually discussing the relative localization of sensor networks. Relative localization is that you have a bunch of sensors that you want to deploy into the forest, and you want to find the optimal location of these sensors, minimizing some mean square error distance between the sensors. However, if you formulate the problem in a 2D space, in the plane, then the problem becomes nonlinear. So it's not really a good motivation. I think it's more interesting the motivation that I was presenting in terms of clock synchronization. Okay, that's all I want to say. Of course, I will be happy to answer questions now or later on.
Yeah.
How do you consider communication delays in the clock simulation problem?
Excuse me?
Communication delays in clock simulation.
Excellent question. In this model, I did not consider explicitly communication delays, but here in principle, I can also take into account some communication delays, for example, embedding here the delays into this eta noise. So in a sense, this noise also includes delay. If you want to explicitly include delays, then you can rewrite it, and then you can also take into account the delay. The question is that, what do you assume about the delay? I guess that you assume that the delay is unknown but bounded within some interval. Then you can also Think about, in the case of additive delay, that you also want to estimate the delay.
I think the delay is always positive and non-zero. And you consider a noise with the
True. In that case, the noise is also takes negative values. Absolutely right. Yes. The protocol that I was showing here does not take into account the delay. So if you really want to take into account the delay, then instead of having Tj here, you can have Tj plus the delay here. This is what actually is done in this PTP protocol. So you can actually embed the delay here. So you can say that the time is not Tj, but is Tj plus tau, which is the delay. I guess that I'm saying that there are possible extensions of the delay case. But it's a very realistic question, it's an important question.
So, what we saw in this model is that we have some similar clustering of the time to the previous problem. Is there any way by, well, including the quote-unquote a stubborn sensor to make them cluster into one single time to provide also...
I see your question.
Yeah.
I never thought about that question. It's an interesting question. I don't know. I actually don't know. It's interesting to see which kind of clustering properties this may have. Nothing that comes out on the top of my head now, but it's an interesting question.
Because if we're interested in some measurements those sensors make and not just the time, we want those measurements to be time-stamped.
Yeah.
And then we have those clusters of timestamps, and then we have relate them to each other somehow.
I see what you mean. It's an interesting question. I never thought about it. I don't know how to address it, but it's an important question.
Thank you very much.
More questions. Roberta, could you explain this name, Byzantine sensor?
Yes.
Why Byzantine?
Well, it's this paradigm that was invented by Leslie Lamport. So it's the city of Byzantium. So there is the city of Byzantium, and so this is the city of Byzantium, and then there is a sultan. This is the paradigm that was used by Leslie Lamport. Leslie Lamport is at UCLA. I think he was at UCLA for a while. Anyway, at some point he got tired of other things, and then he basically said, "Okay, let me do something more useful," and then he produced LaTeX. But anyway, so this problem was invented in the 80s, and so there is a city of Byzantium, and there is a sultan, and then there are several generals around the city of Byzantium. Each general there is a camp, and then the point is that these generals, they want to attack the city of Byzantium, and they want, to maximize the probability of success, and so they want to reach an agreement between them. So it's a consensus problem, if you wish. However, it's a consensus problem, but it's actually a binary consensus problem, because the decision is attack or retreat. And of course, they want to reach some sort of agreement between them. Now, the problem is that, first of all, there are many interesting problems. The first is a clock synchronization problem. So if they want to attack or retrieve at the same time, they should know a global clock. And this is, what is the problem? And also, the point is that there are some of these generals are actually misbehaving. For example, this general actually made some agreement with the sultan. He doesn't really want to attack the city, but he wants to cheat the other generals. And so this is a misbehaved system, which is called Byzantine kind of approach, because of the city of Byzantium, which is what was invented by Leslie Lamport. So it's a way, because, for example, you are on an airplane and you want to measure the altitude of the airplane. And then you have several sensors which are measuring the altitude of the sensor. what is the worst case? The worst case is that one of the sensors misbehaves. But it's not something like a sensor failure, because that's easy to detect. Sensor failure is easy to detect, because then the sensor is no longer transmitting. So there is a signal which is broadcasted by sensor, and then at some point it stops. This is very easy to detect. I mean, the worst case is when this sensor is actually trying to create damage. And this is called Byzantine kind of phenomenon. So it was started by these problems in the 80s, the Byzantine agreement problem, or Byzantine general problems. And then, you know, there were several approaches, and there was this famous, perhaps, algorithm by Rabin, which was basically showing that with probability 1, you can actually reach consensus between this one, assuming that the number of misbehaving sensors or generals is smaller than a certain percentage, which is a very reasonable assumption. Because the problem is that you know that there are some of these generals which are misbehaving, but you don't know who they are. Otherwise, it's very easy to detect them. There are actually people in the control community who are actually using geometric methods, basically algebraic kind of methods, to identify what are the misbehaving sensors. But I actually don't think that that's a reasonable approach. My opinion is more reasonable to say that the number of Byzantine sensors is smaller than a certain percentage, say phi, of the total number of sensors. So this is a very reasonable assumption which was made by Rabin, and under some conditions, Rabin was actually proving that you can reach with probability 1, randomized algorithm works. There was also some other work from that time by some people, I forgot the name now, where they basically proved some what they call impossibility theorem. So basically no deterministic algorithm can be designed for reaching consensus. So only a randomized algorithm can reach consensus with some probability. So anyway, this is the history of this Byzantine agreement. From the 80s in the literature of computer science.
Do you use the full history when you average over the time?
Indeed, yes. This is what we have done, right.
Is it reasonable?
I think it would be interesting to have some sort of smoothing so that you use only part of it. But so far we use the entire history. I think it would be interesting to use only a time window. I don't know if that's possible. It's an interesting question, very interesting question. So far we use the entire history for all the problems.
Maybe it's reasonable to forget about information.
I think that if we have some sort of forgetting factor, it's a very good idea. I don't know the answer.
Okay, no questions. Thanks, Roberta.